Hello everyone, my name is Samuel Lee. This is my Physics 2211 lab number 4, oscillations. So to introduce the lab, the purpose of the lab was to observe a mass on a spring. It swings in an arc, and it's assumed that it's only in the x and y direction, so it's like two-dimensional, right? Doing this experiment allows us to apply Newton's second law and energy principles in a real-life example, and you'll see later on in the lab that the total change of energy of the system does remain at zero, which follows the energy principle. The energy principle is actually one of the fundamental physics principles explored in the lab. So it states that the change in energy is the sum of work done in the system by all the surroundings, which in this case it's assumed to be zero, as in its isolated system. You can see the equation there, the delta K in both potential energies, change in both potential energies from the spring and gravity, they all add up to be zero. And then another fundamental principle is Newton's second law, which states that the system's change in momentum would be proportional to the net force applied. In this case, it would just be the force of gravity and the spring force acting on the object. So to start with our observational model, the system was isolated, as I said earlier. So the system would be the spring, the mass, and the earth. The surroundings would be nothing, doing zero work on the system. The object's trajectory was plotted in tracker, and then the initial for the L naught and the L and the K and everything was given from the video that was the experimental video. And so you'll see those values in the computational model next, but first here's a video of the object in tracker and then the graphs that were obtained from that. You can see the x and y positions of the object, and then you also see that the oscillation of the object in kind of an elliptical motion. These x and y trajectories will be compared to a computational model version, which comes up next here. The computational model was a program in GlowScript. I used a CSV file of the tracker data to compare the two, right? So for the initial conditions, the ball velocity was 0. It was released from rest. The initial position of that was taken from tracker. You can see the code for that there, and then the spring constant L naught was given from the experimental video. You can also see the two values there in the code. And here's a screenshot of the code and the calculation loop. You'll see that the net force is calculated first, then the object's position and velocities are updated using the Newton's second law, the velocity update formulas, and then the changes in the energy of the object were calculated at the end. And then you'll see next here in the screenshot that you'll see the results here. So the graphs from the GlowScript program, you can see that the delta E, the orange line, remains at 0 throughout, which while the sums of the delta K and the delta U of both the gravity and the spring, the sums equal 0, but the different changes in the energies go in that kind of wave pattern, right? You can also see the difference between the model and the experimental x and y positions. The y positions are a bit choppier, most likely due to human error in tracker. But while the x positions, they matched up fairly well, but they're a little offset, which most likely resulted from a difference in the initial parameters between the GlowScript and the observational model. So basically, another reason for this is that there's some work being done on the system in the real world, while because we can't isolate it completely like we can do with the computational model. So to discuss kind of what this means, right? For the model system, is the energy principle satisfied? Yes, the energy principle is satisfied. Although the individual changes in energy are different, the total energy of the system does remain constant, and that shows the conservation of energy, which satisfies the energy principle in this case, as the surroundings did no work on the system. And using the data that we obtained in tracker, I took the average of three different periods that I calculated using the graphs from tracker of the x and y positions. We come up with 1.678 seconds and 1.5 seconds for the x and y positions respectively. The main source they're a little different, right? You can see, but the main source of difference from these values could be from tracking errors when plotting the trajectory, but also the result of them, the differences. It would change the graphs and then the calculated spring constant as well. And as usual, there's a lot of errors that could be happening in the lab. I mentioned this a lot, but human error within tracker when plotting the object's trajectory. There could have also been errors in the code of the computational model. And then any work done on the experimental system that accounts for kind of the discrepancy and the differences between the two models' different results here. Thank you very much.